Okay, so, okay, shut up now. This is my time. I have to listen to people 23 hours a day, but this is my time. Okay, well, not when I sleep. I don't really listen. We have a quiz at the end of class, and before that, what I would like to do, we have, well, so what do we have coming up? We have exam 2 coming up a week from today. So what's that, November 3rd, I think? And if you can't make it to the Thursday class, but you can make it to the Wednesday class, feel free to do that. That's always fine. The topics are going to be everything up through free body diagrams. So you'll have a lecture video before. Well, I guess I actually just posted it yesterday. So there's a lecture video now with some problems where you're doing Newton's second law, but that's not going to be on the test. All you have to do on the test is draw free body diagrams and everything before, Remember that these tests are cumulative, so you need to refresh your memory on the old stuff. Any questions about the test? Yes?
Is it good to look at the weekly assignment too?
Yeah, those are, the daily problems and the daily problems and the weekly problems are your two best indicators of what kind of questions are going to be on there. Yep, for sure. And so if you have time, go through some of those old problems. What I would recommend doing is go back through the daily problems and just ask yourself, do I know the steps of how to do this? You look at the problem, you're like, oh yeah, you do this, this, this. Then there's not really any reason to waste any more time on that. But when you get to the problems where you're a little hazy on it, those are the ones that you might want to work back through, look back at the solution. I think that's the best way to get ready for it. Okay. Any other questions? And you can also, so I said the daily problems and the weekly problems, but also any example problems that I've done in class or in the lectures or whatever, those are also, I think all of those are tend to be at kind of the same level, and they're all aimed at trying to get you ready for the kind of problems I'll put on the test. So that's all good stuff to look at. And then the next thing we have coming up is lab exam 2. A lot of you still have lab exam 1 to take because I lost your exams. No, I'm just kidding. I'll fix that. Okay, but this is the week of November 7th. So not next week in lab, but the week after. And the topics for that, it's everything that we've done so far. So it won't be anything from next week. I'm still thinking about whether we're going to have a new lab next week or not. But the topics are everything up through 2D acceleration. Any questions about that? For the people who have your lab on Thursday, who have it today, the thing that we're doing in lab this week is just a review of all this old stuff. So hopefully that'll be a good lead in for the lab exam. Okay, so now what I want to do today is just go over some old problems, some of the recent stuff. I'm not going all the way back to the beginning, But I'm going to write some problems up here. I'm going to pause the video, give you time to work through it, and then I'm going to work through it so you can compare your answers, make sure that you're sort of on the right path with this stuff. I'm going to do a vector problem, one or two two-dimensional kinematics problems, and then a couple of free body diagrams. Okay. Today, I'm doing examples for exam 2. So for the first one, this is a vector problem. So let's say that you have a vector that has a magnitude of 10 and makes an angle of 40 degrees with the vertical. So first, what are the components in a coordinate system oriented this way with the positive x-axis to the left and the positive y-axis down? And then second, what are the components of that vector in a coordinate system with the x-axis down and the y-axis to the right? Okay. So take a couple minutes and okay. So here's how to do this one. So draw out the coordinate system in the orientation that's given. And the key thing is, so that coordinate system can be at different orientations, but you don't ever change the orientation of that vector. You just take that, like, if your pencil and paper had a thing where you could just copy and paste, you're just copying and pasting the tail of that vector onto the origin of this coordinate system. So this goes here, and we know that this angle is 40 degrees. Okay, and so now the key thing that you need to figure out is what's the counterclockwise angle from the positive x-axis to the vector. So this angle is, the theta that we want. And you can see that that's 90 plus 40. So 130 degrees. This length is 10. And so the components are 10 times cosine of 130, 10 times sine of 130. And that is negative 6.43, positive 7.66. And second, so now the coordinate system has the x-axis down. Is that what it was? Yeah. And the y-axis to the right. Copy and paste that vector. This angle is still 40 degrees. So the angle theta that we want goes from the positive x-axis of whatever coordinate system you're using. Like, I think something that's confusing for a lot of people is you're like, okay, well, the real x-axis, like the real x-axis is pointing to the right. This sort of pretend x-axis is down. But the way to think about it is there's no real x-axis. There's only you only feel that way because you're most used to that one. But in this problem, the x-axis is down. So what you want is the counterclockwise angle from that x-axis to the vector. In this case, that's 40 degrees. So the answer is 10 times cosine of 40, 10 times sine of 40. And that is 7.66, 6.43. Okay, so here's example 2. This is a 2D kinematics problem. So say this is a motorcycle jump. I'm changing the numbers from yesterday because the ones I used yesterday would definitely get this guy killed. Yeah.
Yeah, one question on the first one.
Yeah.
Is cosine always for x and sine always for y?
Yes, always if you're measuring your angle from the positive x-axis. You can also come up with those angles by making right triangles with whatever axis you're near, and then you have to think more. You have to use SOHCAHTOA to figure out what sine and cosine you want. But I think this is easier. Okay, so let's say this is 30 degrees, and this is the motorcycle jumping. I'm not really a great motorcycle artist. This guy is going to land on a ramp, and the landing height is going to be the same as the takeoff height. Let's say that height is 3 meters. And let's say that the speed at takeoff is 25 meters per second. So 2 questions. First, what's the motorcycle's height at its highest point? And then second, how far away horizontally does the ramp have to be? And just because I've slowed this down a little and lowered it a little from yesterday doesn't really mean this is safe. Okay, go ahead and work on that one. Talk to each other, ask me questions, and then when you're done, I'll go through it. Do this now. Okay, so what's the first thing we have to do for part A? We're trying to find the highest point. In these constant acceleration problems, what's the first thing you have to do? You have to choose instants for time equals 0, time final. You have to choose an origin location and a coordinate system orientation. These two I'm just going to show on the picture. So you can get the right answer using any choices of these you want, but I'm going to do what I usually do, which is put the coordinate system on the ground below where the object is at time equals 0. And my y-axis is going to be up. Okay. So that's the coordinate system. What about the instants? So these are the ones that there's no flexibility on. Rarely is there any flexibility on these. So time equals 0, what's that going to be? You have instant that it leaves the ramp. And then time final, what's that going to be? For part A, it's going to be, so for part B, it's going to be when it hits the other ramp. For part A, it's going to be when it reaches the highest point. So now we can figure out what we know and what we want. Do we know time final? So we chose a time equals 0, and we chose a time final. We chose the instance to turn on and turn off the stopwatch. Do we know what the stopwatch says? We don't. If we could get by without it, we're fine with that. So I'm just going to leave that off for now. Do we know the acceleration? Yeah, in free fall, we always do. So that's 0 for x and negative 9.81 for y. What about while he's on the way up? What's the acceleration? Same. What about when he's on the way down? Same. No matter what, the acceleration is the same. It's only the velocity and positions that change. Do we know the initial position? Yeah, I put the origin right underneath the takeoff point, right underneath the point at time equals 0. So x is equal to 0. And what's y? 3, yep. Do we know anything about P final? We don't know that. We know the something about the velocity at the highest point, but we are trying to find PFY. Okay, PFX we don't care about. Maybe we'll find it. Possibly we'd find out later that we needed to get it to solve the problem, but for now we don't care about it. What about the initial velocity? How do we get that? Yep.
25 cosine sine 30.
Yep, exactly. So the takeoff angle is 30 degrees. So 25 times cosine of 30, 25 times sine of 30. And you get 21.65, 12.5. And then do we know anything about the velocity final? We know one thing. We know, and this is anytime you hear a question that says something about the highest point, you should think, okay, I'm going to use the fact that the velocity at that instant, the y component of the velocity is equal to 0. That's like the defining feature of the highest point. So VFY is equal to 0. Is there an equation that works with these? I think the one that does is 2 times AY times PFY minus PIY is equal to VFY squared minus VIY squared. And I'll give you all those equations on the test. So 2 times negative 9.81 times this PFY that we're trying to calculate minus PIY is 3. VFY squared, that's 0 squared, minus VIY squared, so that's 12.5 squared. Notice you're not squaring that negative sign. That would make it positive, and that would mess everything up. So we have negative 19.62 PFY and then plus 2 times negative 9.81 times negative 3 is positive 58.86. And that's equal to negative 156.25. So subtract 58.86 from both sides, divide both sides by negative 19.62, and you get that PFY is equal to 10.96 meters. I have one little thing to say about that answer. The question is, what's the height at the highest point? That means what's the distance off the ground, okay? If you had chosen your origin of your coordinate system at a different height that's not on the ground, you would have to, you can do that and you would get a final answer for your PFY, but then you'd have to take into account that it's measuring from something other than the ground, okay? So like another good choice, common choice for this would be to put the origin at the takeoff point. You would have done all these calculations and gotten a height of 7.96, but that's not the height. So then you would have to add that extra 3 in because you're starting from 3 meters off the ground, okay? Would I take off a point for that on a test? Probably not. But you have to remember stuff like that. The question is asking, it's a very specific wording about what it's asking for, and you have to take that into account. Okay, for part B, so now it's asking how far the thing goes horizontally before it hits the down ramp. Again, we have to start with this. A lot of times for parts A and B in a problem, you'll use the same choices for the origin and the time equals 0 and everything, but that's not always the case. So you have to ask yourself whether you can use the same things or whether you have to change them. We can keep these the same, and I don't think there's really any reason to change those. So, but what about the 2 instants? Is there any reason to change the time equals 0 instant? No, that works fine. You could probably make it work. You could probably change it to when it's at the highest point, but that seems unnecessarily complicated. So let's keep this the same. But our time final has to change because you can only calculate things that are at one of your 2 instants, So, and we're trying to calculate something when it lands. So this has to be the instant that the motorcycle lands. And that's going to change a little bit about what we know. Okay. So let's think again about what we know, what we want. Since our coordinate system and everything is the same and our time equals 0 is the same, all of our initial stuff is still going to be the same, but our final stuff, anything we knew there is going to be different. Do we know what the stopwatch says? No. If we can do it without solving for that, that's fine, so I'll leave it off for now. The acceleration is free fall. So this is 0, negative 9.81. Do we know the initial position? Yeah, that's the same as it was before. So that's 0, 3. Do we know anything about the final position? Well, we know that the 3 is right. We know that PFY is equal to 3. We don't know the horizontal position, and actually that's what we're trying to find. The initial velocity is the same as it was before. 21.65, 12.5. And then do we know anything about the final velocity? No. Really deep down, we know that the x component of the velocity isn't going to change. But you don't want to put that in your list because it'll suggest equations are going to work, but then when you do them, everything will cancel and it won't help you out and you will have wasted 42 seconds or whatever, you know. So we'll just leave it off. All right, so is there an equation that has pfx in it and everything else is here? For this one, there's not. So when that happens, what do you try to do? So yeah, no equation works. So we're going to have to find TF. We're going to have to figure out what the stopwatch says. And to do that, we'll use the equation PFY is equal to PIY plus VIYTF plus 1/2 AYTF squared. Sometimes it's a little bit of a pain to solve for t using this equation, but a lot of times it's the way you have to go. You can see it's a little bit of a pain because the t is quadratic. So sometimes you have to use the quadratic formula. Sometimes stuff just cancels out and you can factor it easily or whatever. Okay, so we get 3 is equal to 3 plus 12.5 TF minus 4.905 TF squared. These two cancel. And so you can write this as 4.905 TF squared is equal to 12.5 TF. Now remember, any equation where you're solving for something squared is going to have two solutions. Okay. You could use the quadratic formula to find this, or you could cancel one t, divide both sides by TF, and you just get that 4.905 TF is equal to 12.5. Now, all of a sudden, we're only going to have one solution here. What's the solution that we eliminated when we divided both sides by TF? Often it's a negative solution. In this case, the solution is just 0. You can think of it as like we're factoring out a TF, and we have 12.5 minus 4.905 TF. And so the two ways that this can end up being 0 is if TF is 0 or TF is 12.5 divided by 4.905. The thing in the parentheses is equal to 0. Okay, so TF is 12.5 divided by 4.905. So that is 2.55. What is it? So I guess I didn't sort of finish that thought. That second solution, what does it mean physically? The solution when time is equal to 0. So it means, it's telling us our two solutions are at our time equals 0 and at time equals 2.55. Why is time equals 0 one of the solutions? There is a solution. It's actually saying that what we're looking for is when the height is 3 meters. And the height was also 3 meters just as it was leaving the ramp. But that's not the one we care about. So getting rid of that one didn't cause us a problem. Okay, now we have TF. Now hopefully we can use that to solve for the thing we wanted, which was PFX. And yeah, we can use the X version of that same equation Okay, so Pfx is equal to 0 plus 21.65 times 2.55. And then this is something that people, I think, especially with the pressure of the test or whatever, get wrong a lot. What's AX? It's 0. I know you're used to thinking in free fall that the acceleration is negative 9.81, but remember the X component is 0, so this whole thing goes away. So Pfx is equal to 55.21 meters, which is 200 feet, 180 feet or something. Is it a good idea to jump your motorcycle 180 feet? In my opinion, it's not. That's a decision you're each going to have to make for yourselves. Any questions? Okay, well, let's go to some, let's get at least one free body diagram problem. Let's do 2. Let's get 2 in. So problem 3. So let's say that you have a ramp and there's a 5 kilogram block on the ramp. And at this instant, the block is sliding down the ramp. So like that's the direction of the velocity vector. And the coefficient of friction between these two is 0.2. Draw a free body diagram of the block. Okay, so the first step is just drawing the outline. Then the weight force is always straight down at the mass times 9.81, so 49.05. And then now we're going around the boundary looking for contact. The only contact with the boundary is at the ramp. And so there are 2 things going on with a contact when there's friction. There's the friction force itself, and there's the pushing contact. The pushing contact, the rule is perpendicular to the surface, toward the chosen body. I'll call that N. And now the friction force is opposite of the velocity vectors. It's opposite the direction of motion. And the magnitude is the coefficient. That's 0.2 times N. If this had been sliding up the ramp at this instant, like right before this instant we're looking at, it had been given a big shove and it's still sliding up the ramp. The only thing that would change is that friction force would be the other direction. Okay, so let's do one more problem where we get in the other 2 types of forces, of contact forces. So let's say there's an incline with a pulley. And let's say this has a mass of 2 kilograms and it's connected over the pulley by a cable to a 1 kilogram hanging mass. The wheels are there to suggest that there's no friction there, so you don't have to worry about friction. But do free body diagrams of each of these two. Okay. Okay, let me go through this. So first I'm going to do the hanging mass, the 1 kilogram mass. My mom says you should listen because I'm special. Okay, so the weight is 1 kilogram times 9.81. Now go around the boundary looking for contact. The only contact force is that pulling contact from the cable. So the rule for that is the force is parallel to the cable, away from the chosen body. And I'll label that T. That's a pretty standard thing to call that variable. And then for the cart, okay, there's a weight force. That's 2 times 9.81, so 19.62 newtons. There's a contact force from the ramp. And the rule for that pushing contact is perpendicular to the surface toward the chosen body. Oh, how can you tell the difference between a pushing and a pulling contact? How can you tell which is which? A pushing contact is keeping two things, it's the thing fighting two things from merging, from invading each other's space. And a pulling contact is keeping things together, So like the cable, if you cut that cable and eliminated that force, these two things would fall farther apart. If you turn that ramp into water, quicksand, whatever, that cart would sink into the, so that's how you know that the cable is applying a pulling force and the ramp is applying a pushing force. So I'll call this N, that pushing force from the ground. And then the only other contact with the boundary is the cable. And so the rule is parallel to the cable, away from the chosen body. Since it's the same cable as we had over here, just going through pulleys, this label has the same name. Any questions about that? Yeah.
Does it matter when you put like the base of the arrow inside the object versus outside?
Nope, it doesn't matter. Remember, the location of vectors doesn't matter. They're just a magnitude and a direction. Yes? On your drawing? Yes, get in the habit of drawing it in the right orientation. If anything, exaggerate the angles. You should be able to tell, ideally, from the free body diagram, what vectors are parallel and what vectors are perpendicular and what vectors are neither. You know what I mean? So even if something's at a 10-degree angle, you're sort of best off drawing it sort of at 45 degrees to really accentuate that angle difference, Any other questions? Yes?
For the pushing force on the cart off the ground, sometimes on the videos you label it like 1, 2, 3.
Yeah. Okay, because the pushing contact on individual bodies doesn't have to be the same, right? There's no reason it would be the same. So you have to give them different names, and you could call it N, R, X, whatever. They're just variables, but those subscripts just make them different variables. The only time that's not true is when you're talking about the pushing force between two bodies. Then the one on, say, the top one has to have the same variable name as the one on the bottom one. They're just in opposite directions. Okay, let's do the quiz. Shouldn't take too long.